Hi, and welcome to this video where we continue our study of methods for representing text for machine learning. In this video, we'll look particularly at co-occurrence matrices. So let me just recap what we're looking at. We're looking at applications where we would like to do machine learning on text, for instance, building a spam filter that can take a given email and determine whether this email is spam or not. And the issue is that we have to find some way of representing this text so that we can feed it into one of the machine learning models we've seen so far. And for doing this, we saw, for instance, the very first representation was the so-called bag of words representation. So if I have a text like the spam email that I received here, if I want to give a bag of words representation, then I'm going to assume, at least for now, that all the words come from the English dictionary. And then the way I'm going to represent the text is I'm going to create a vector that has one entry for every word in the English dictionary. For instance, has an entry corresponding to agra, potency, cow, and so forth. And then every entry in this vector stores the number of times that this word occurs in the text that I'm representing, right? So it's just a long vector of counters of the number of words, of occurrences of every word in my text. So that's the bag of words representation we saw in one of the previous videos. We also saw the tf-idf representation. So one issue with the bag of words representation was that, common words like and the and so forth, they will get large counts and they'll be in all the documents. And this might kind of make it more difficult for the downstream analysis because the vectors will have like many coordinates that are large and that are in common to all the vector representations of documents. Now, the tf-idf representation tries to deal with this by introducing this factor here that kind of the IDF or inverse document frequency factor that tries to account for the fact that some words are more rare than others. So given a training data set of n documents, for any word or term, it's called here, you count how many of the documents that contain the term, and then you weigh the count of this term by this log of the fraction of documents containing the word, so a rarity score in some sense. Like the more rare it is, the larger weight it's given. And you also normalize the count, number of occurrences of a word in the document by the length of the document to account for different length of document lengths. Okay. So this is one of the representations that we've seen so far. Now, an issue with both of these representations is that they kind of ignore similarity between words. Like, for instance, the word man, boy, woman, girl, they're kind of, at least as humans, we think that these are closely related, these words. But in these two representations above, they're not really treated differently from one another than they are from apple, football, and this. Like every word in some sense is just a different coordinate in the feature vectors. So if we want to try and formalize this a little bit, let's just try to look at this bag of words representation again. And then let's see that we can also think about it in a slightly different way. And another way to think about the bag of words representation of a document is to think about, well, let's say that every word in the dictionary is represented by a concrete vector. Now, in bag of words, what does this mean? Right, so what we say is that every word or term, it will correspond to a standard unit vector. So the vector corresponding to the word or term t is just the standard unit vector. So this is a vector that has a 1 in coordinate t and zeros everywhere else, right? So it's basically just and it just tells us what is the coordinate corresponding to this word. And if you think about what the bag of words representation is doing with the document, well, it's representing the document d as a vector v of d. And the way it's doing it is it's just summing up the vectors corresponding to all the terms that occur in the document, right? Because this is just summing up every time I see the word t, I'm just adding the standard unit vector et, so which means that when I'm summing them up, the final vector v of d will just have in the coordinate corresponding to t, it will just store the number of occurrences of t in that document, right? So it's just another way of thinking about what is bag of words doing. It's just having a separate standard unit vector for every word in the dictionary, and then you're summing up the standard unit vectors corresponding to the words that occur in your document. So this is another way of thinking about bag of words. Right, so let's just try to be completely formal just so that it's clear here, right? So let's say I have this text here that I received as an email. And now let's say I want to think about the bag of words representation, right? The bag of words representation is just this one, right? For every word, you have a counter of how many times it occurs, right? So for has a count of 1, can has a count of 1, who, abroad, and partner. They all have a count of 1 here. And then words that do not occur in the text don't have any counts. But if you think about it, then you can also have thought about it as the following, right? We have a vector, a standard unit vector for the word for. It just has a 1 in the position for and zeros everywhere else, right? And you can have the word for can has a 1 in the coordinate corresponding to can, and so forth. So these are all the standard unit vectors. And we can also think of obtaining V of D as just summing up these standard unit vectors corresponding to the words that occur in the document. That's another way of writing it. Okay, so if we go back to this issue that the similarity between the words are ignored, and then one can also see it by looking at these vectors that represent each of the words in their own, right? So the vector representing the word man is just a standard unit vector with a single 1 in the coordinate corresponding to man, 0s everywhere else. Boy has just a 1 some other position corresponding to boy, and the inner product between these two vectors is 0. And that's the same as the inner product between the vector representing man and the vector representing this. And also this means that the distance, because they're all unit vectors, the distance between the vector representing woman and the vector representing girl is just the same as the vector or the distance between boy and apple, right? Even though you would in some sense think that woman and girl are closer related than boy and apple is. So that's one way of seeing that these vector representations that we use in bag of words, they don't really capture word similarities, right? You would actually have liked that the vector for woman and girl was somehow closer to each other than boy and apple, right? So this is what we'll try to address using these co-occurrence matrices. Right, so in some sense, our intuition is that it would be nice if the vector representation of a document D was similar to the vector representation of a document D prime. If we took all the words in D and replaced them by synonyms, right? So words that basically have the same meaning, that gives us D prime, we would actually have liked that these two representation of these two different documents would be basically the same, because the meaning of the text should be basically the same. So the question is, of course, how can we define word vectors so that when we sum up the vectors corresponding to all the words in the document, then we get similar document representations. So we want really word vectors that preserve similarities between words. So these are so-called word embeddings. So from here on, we're going to look at how do we embed words. And then if we want to get the embedding of a whole text or document, we can just sum up the word embeddings for all the words in the text, in the document, right? So we want to look now at embedding words individually. Okay, so we would like somehow to define some word vectors that preserve similarity between words. So here's a bunch of words, and this is really an unsupervised learning problem in some sense, right? We just have words. There's not really a notion of labels. There's just different words. There's no one telling us that this is more similar to that one. So what we want to do is we want to use unsupervised learning. That's the basic idea, to learn similarities between words from some data set that we collected. Right? So we don't want as a programmer to sit and write down this word is similar to that word. We'd like to learn these similarities from data. So there's no labels here. There's just text, like lots of text data, and we want to use this text data to learn which words are similar. Right, so for instance, we would like to learn that somehow all these words are fruits and all these words are tech companies. And so these tech companies should have more similar word embeddings than the embeddings of the fruits. Right, so, and the first thing we'll see, and what we'll look at in this video, is co-occurrence matrices, and we'll see more advanced things in the next video. But the basic idea is to base the similarity between word embeddings, so the vector representing different words, on occurring in similar sentence structures, so together with similar words. So to formalize this, we'll use two concepts, a co-occurrence and a context window. So let's again look at this sentence here. Now, the context window is something that's specified by a width around a word. So for instance, we can look at the context window of width 2 around the word who in this text. So the context window now is, so the word who is the one we're looking at. The context window is the two words preceding it and the two words following it in this text. Now, a co-occurrence now, given such a context window, is that we say that we have now a co-occurrence between who and every word in the context window around who. Right, so we have the co-occurrence who with partner, who with abroad, who with can, and who with accommodate. Like those are all co-occurrences that we have from this context window here around the word who. So right? And also we can also look at the co-occurrences resulting from the context window around can. So here we get the co-occurrence can with abroad, can with who, can with the common date, and can with 200 million. And so these are all co-occurrences once we've specified a context window of width 2. Now, a co-occurrence matrix now is defined from a set of training documents. So we have some data, D1 to Dn, so it's a lot of training documents, lots of text. Maybe we've collected a lot of emails, and maybe we've gathered all of Wikipedia or something similar. And now in this matrix, we're going to have an entry for every pair of words, T1 to 2. And this entry just stores the number of counts. It counts how many times did we have a co-occurrence between these two words in all of this training data, D1 to Dn. So let's say our training data, just for simplicity, just consists of 3 documents, these 3 down here. Apples taste good and are healthy. The taste of pears is delicious, and basil adds a good taste to the dish. Right? So these are 3 different documents. And so the co-occurrence matrix that we will construct would now have a row for every word and a column for every word. And what we're storing in these entries here is, well, basically this is the co-occurrence matrix here. And what we're storing is the number of co-occurrences. So here we can look at the number of co-occurrences between good and taste, right? So we look at, in this row, we look at all the context windows placed at occurrences of good. So there are 2 occurrences of good. And we look at those context windows and we see how many times in this column does it co-occur with taste. And so it does so in both these cases, right? So the 2 co-occurrences between good and taste. Similarly, if we look at apples and taste, we look at the context windows around apples. There's 1 occurrence of apples, and in the context window here, it co-occurs with taste. So we have a co-occurrence count of 1 here. Right. So now with this co-occurrence matrix defined, what we'll do is with our word embeddings is that we will take a word T, and then we will embed it as just as the row in the co-occurrence matrix, the corresponding row. So this would be if I want to embed the word apples, right? So if I want the vector representation of the word apples, it'll be this vector that just gives the row in the co-occurrence matrix, right? And also this would be the embedding of pairs. And at least in this case here, you can see that they're a little bit similar, right? They both occur together with the word taste, but not completely equal. They don't occur together with the word good in this case. But the intuition is that the basic idea with this co-occurrence matrix is that apples and pears, they will have similar rows, or at least more similar rows than, for instance, apples and cars, basically because apples and pears occur, for instance, more often together with words such that taste than a car does, for instance, right? Or eat, perhaps. Both apples and pears occur more often together with the word eat than car does. So in some sense, right, if words occur together with similar words across all these documents, then they have more similar rows in this co-occurrence matrix. So that's the basic idea in the co-occurrence matrix. So the embedding now of a word is just take the row corresponding to this word in the co-occurrence matrix. The problem is these are very long vectors still. If you think about it, well, they're still basically proportional to the size of the dictionary, right? There's a column for every word in the dictionary. There's a row in every word of the dictionary. So it's a fairly long vector representation. And I don't know, maybe we can use all these feature hashing tricks that we saw in some of the previous videos afterwards if one wanted to. Right? So you can use dimensionality reduction. And what I'll show here is that one of the most popular approaches is based on principal component analysis, right? So this is very similar to what we've seen previously. So this is not exactly the PCA approach that we've seen before, but this is going to be similar to PCA. So what we're going to use here is that this co-occurrence matrix, it is symmetric and real, right? So it's symmetric basically because if some word co-occurs with another, you can place the context window at this other word, and at least if it's symmetric, the width of the context window to, for instance, 2 words preceding it and 2 words following it, then it will be symmetric. And also, obviously, it's a real matrix. So as we did in the principal component analysis video, we can also do an eigen decomposition of this co-occurrence matrix. So just to remind ourselves of these facts, right? So an eigen decomposition is if I have a real symmetric n by n matrix A, then you can write it as E times D times E transpose, where E is a diagonal matrix the ith diagonal entry is equal to the ith largest eigenvalue of A, and this eigenvalue is called lambda I. And this matrix E is an orthonormal matrix, meaning that its columns and rows are unit length, and the columns are orthogonal, and so are the rows. And the ith column of E is just the unit length eigenvector mu I corresponding to the eigenvalue lambda I. And the definition again of eigenvalues and eigenvectors is that if I take A and multiply it with mu I, I'm going to get lambda I mu I. Right? And if this is a real symmetric matrix, then the mu I and the lambda I are all real, so they're not complex vectors. Right? So this is just a fact, and we'll be using this. So the eigendecomposition will take the co-occurrence matrix, call it X, and then we'll write it as E d transpose, E d E transpose. Sorry, so E was this, the column vectors are the eigen vectors. The diagonal matrix D has eigenvalues on the diagonal, and here we can assume that they're ordered such that in absolute value, the largest one is lambda 1, which is greater than or equal to lambda 2, greater than or equal to lambda 3, and so forth. Maybe just if one remembers the PCA video, there we also had that the matrix that we did an eigendecomposition of was also a PSD matrix, positive semi-definite. So there we actually had that all the eigenvalues were non-negative. Here we just we order them by absolute value. The norm of all these mu i's is 1, and the inner product between them is 0. So that's what we have in this eigendecomposition that we can compute for the co-occurrence matrix. Now, what we can observe now is that, so we can write our X now in this product here, right? So we have the E, we have the D, we have the E transpose. So this matrix here is D by D. Right? If there's D, if D here denotes the number of words in the dictionary. Now, what we're going to do is, like we did in PCA, we're going to we want to reduce the dimensionality. So in some sense, we want to keep only the top k eigen values and the corresponding eigenvectors. So the basic idea when you have this representation is to say, okay, I'm going to change the matrix a little bit, or change the representation by setting all but the first k eigenvalues here. I just zero them out, right? So I keep the first k and I zero out the rest. Then I get something that's not the original X, which is some approximation of the original X, right? So I get another matrix here, the resulting from multiplying these three. And what we see here is that everything here is unchanged if we delete all but k of the columns of E, right? So what I could do now is I could just say, like, if you look at this product up here, right, because I have zeros everywhere but the first k, this basically corresponds to zeroing out all but the first k columns of the first matrix and all but the last k rows of the last matrix here. So that's what I've done here. Now I only kept basically the first k columns of the first matrix and the first k rows of the last matrix. And now it's a D by k, k by k, k by D matrix, right? This is the same product as up here. And so this is basically an approximation of X. I'm basically approximating X by this product here, which is a little bit similar to PCA in some sense. And now if I just want to embed my words now, what I'm going to do is I'm going to ignore this last matrix here. Right, so in some sense, it's a little bit similar to writing it in this basis corresponding to mu1 to mu k, kind of, but we're still keeping some of the eigenvalues. So this is the basic approach that we're just going to basically, we take this eigendecomposition of X. Now we delete the last matrix here. We take the diagonal matrix D and we only keep the top k by k corner. And for the first matrix E here, we're just going to keep only the first k columns of it. And now this is a D by k because the last one is a k by k and this is a D by k. So this product here is the D by k matrix. Right? And this is our representation. This is our approximation of X. So we're going to approximate X by a D by k matrix corresponding to the k largest, the k eigenvectors corresponding to the k largest eigenvalues and absolute value of X. We're just going to keep those columns and we're going to keep those eigenvalues as well in the diagonal matrix, which we multiply onto it. And this means now that this is a D by k matrix, so it has a row for every word. It has only k columns. So the rows now, or the embeddings of the words, are only k long, right? So this means that if I want to embed a word now, I'm still going to take this D by k matrix and I'm just going to pick the row corresponding to my word. That would be the embedding of my word, right? And if you want to do this in practice, you typically choose k maybe in a couple of hundreds or something like this. Right? So a couple of hundred columns left in this matrix. So right? So just to summarize what this co-occurrence matrix is doing for the training documents, you just compute this matrix that stores all these counts, has an entry for every pair of words, count the number of co-occurrences, mean the number of times that there's a context window around each of the words where they both occur inside. And then we can do an eigen decomposition of this matrix. It's an original D by D matrix if you have D different words in the dictionary, and we replace it by a D by K matrix. And this is using these largest eigenvalues of the matrix. And then we can use these as representations of words. And recall again, if I want to represent a whole document, then I just sum up the vector representations of all the words that occur in the document, right? So these rows would now be my embeddings of my words. The main issue with this representation is just that it can be slow, at least to compute an eigen decomposition on a large matrix, right? If you think about it, let's say that this matrix has maybe 100, if there's 100,000 different words occurring, it's 100,000 by 100,000 large, this matrix, right? So it could also be very memory heavy just to compute the eigen decomposition, just even to store this matrix. It can be quite intensive. So we'll try to see in the next videos there's some other alternatives to using this co-occurrence matrix, but this is one approach that one can use.